So, so yeah, this is the timetable. In contrast, the orange least square lines is relatively flexible. Okay, what is this?
Short term memories.
Fuck's sake.
I've got them both. Oh, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about long short term memory, LSTM, and it's going to be clearly explained.
That, Dan? Yeah.
Always be curious. Radiant problem. If not, check out the quest.
I'm gonna look at the timetable. 2, 2, 2. 8 hours. 10 hours. Fuck yeah.
Also note, although long short-term memory is totally awesome, it is also a stepping stone to learning about transformers, which we will talk about in future stat quests. In other words, today we're taking the second step in our quest. Now, in the stat quest on basic, vanilla recurrent neural networks, we saw how we can use a feedback loop to unroll a network that works well with different amounts of sequential data. However, we also saw that when we plug in the numbers, when the weight on the feedback loop is greater than 1, and in this example, the weight is 2, then, when we do the math, we end up multiplying the input by the weight, which in this case is 2, raised to the number of times we unroll the network. And thus, if we have 50 sequential data points, like 50 days of stock market data, which isn't really that much, then we would raise 2 by 50. And 2 to the 50th power is a huge number. And this huge number would cause the gradient, which we need for gradient descent, to explode. Kaboom! Alternatively, we saw that if the weight on the feedback loop was less than 1, and now we have it set to 0.5, then we'll end up multiplying the input value by 0.5 raised to the 50th power. And 0.5 raised to the 50th power is a number super close to 0. And this number, super close to 0, would cause the gradient, which we need for gradient descent, to vanish. Poof. In summary, basic, vanilla recurrent neural networks are hard to train because the gradients can explode, kaboom, or vanish. Poof. The good news is that it doesn't take much to extend the basic vanilla recurrent neural network so that we can avoid this problem. So, today, we're going to talk about long short-term memory, LSTM, which is a type of recurrent neural network that is designed to avoid the exploding/vanishing gradient problem. Hooray! The main idea behind how long short-term memory works is that instead of using the same feedback loop connection for events that happened long ago and events that just happened yesterday to make a prediction about tomorrow, long short-term memory uses two separate paths to make predictions about tomorrow. One path is for long-term memories, and one is for short-term memories. Bam! Now that we understand the main idea behind long short-term memory that uses different paths for long and short-term memories, let's talk about the details. The bad news is that compared to a basic vanilla recurrent neural network, which unrolls from a relatively simple unit, long short-term the bad news is that the idea behind long short-term memory that uses different paths for long and short-term memories, let's talk about the details. The bad news is that compared to a basic vanilla recurrent neural network, which unrolls from a relatively simple unit, long short-term memory is based on a much more complicated unit. Holy smokes, this looks really complicated. Don't worry, Squatch, we'll go through this one step at a time so that you can easily understand each part. Bam! Note, unlike the networks we've used before in this series, long short-term memory uses sigmoid activation functions and tan-H activation function. So let's quickly talk about sigmoid and tan-H activation functions. In a nutshell, the sigmoid activation function takes any x-axis coordinate and turns it into a y-axis coordinate between 0 and 1. For example, when we plug in this x-axis coordinate, 10, into the equation for the sigmoid activation function, we get 0.99995 as the y-axis coordinate. And if we plug in this x-axis coordinate, -5, then we get 0.01 as the y-axis coordinate. In contrast, the tan h, or hyperbolic tangent, activation function takes any x-axis coordinate and turns it into a y-axis coordinate between -1 and 1. For example, if we plug this x-axis coordinate 2 into the equation for the tan h activation function, we get 0.96 as the y-axis coordinate. And if we plug in this x-axis coordinate, -5, we get -1 as the y-axis coordinate. So, now that we know that the sigmoid activation function turns any input into a number between 0 and 1, and the tan h activation function turns any input into a number between -1 and 1, let's talk about how the long short-term memory unit works. First, this green line that runs all the way across the top of the unit is called the cell state and represents the long-term memory. Although the long-term memory can be modified by this multiplication, and then later by this addition, you'll notice that there are no weights and biases that can modify it directly. This lack of weights allows the long-term memories to flow through a series of unrolled units without causing the gradient to explode or vanish. Now, this
What would you recommend? How do they go about day-to-day sort of specific advice about learning in the world of deep learning machine learning?
Getting the habit of learning is key, and that means regularity. And for myself, I've picked up a habit of spending some time every Saturday and every Sunday reading or studying. And so I don't wake up on Saturday and have to make a decision. Do I feel like reading or studying today or not? It's just what I do. And the fact is a habit makes it easier. You know, just like we brush our teeth every morning. I don't think about it. If I thought about it, it's a little bit annoying to have to spend 2 minutes doing that, but it's a habit that it takes no cognitive load. But this would be so much harder if we have to make a decision every morning. And actually, that's the reason why I wear the same thing every day as well. It's just one less decision. I just get up and wear my blue shirt.
What would you recommend? How do they
Retarded. Too much. This is too much too.
Is a test observation drawn.
pink line, called the hidden state, represents the short-term memories. And, as we can see, the short-term memories are directly connected to weights that can modify them. To understand how the long and short-term memories interact and result in predictions, let's run some numbers through this unit. First, for the sake of making the math interesting, let's just assume that the previous long-term memory is 2, and the previous short-term memory is 1. And let's set the input value to 1. Now that we have plugged in some numbers, let's do the math to see what happens in the first stage of the long short-term memory unit. Let's start with the short-term memory, 1 times its weight, 2.7. Then we multiply the input, 1, by its weight, 1.63. And then we add those two terms together. And, lastly, we add this bias, 1.62, to get 5.95, an x-axis coordinate for the sigmoid activation function. Now we plug the x-axis coordinate into the equation for the sigmoid activation function, and we get the y-axis coordinate, 0.997. Lastly, we multiply the long-term memory, 2, by the y-axis coordinate, 0.997, and the result is 1.99. So this first stage of the long short-term memory unit reduced the long-term memory by a little bit. In contrast, if the input to the LSTM was a relatively large negative number, like -10, then, after calculating the x-axis coordinate, the output from the sigmoid activation function will be 0. And that means the long-term memory would be completely forgotten, because 0 and 1, the output determines what percentage of the long-term memory is remembered. To summarize, the first stage in a long short-term memory unit determines what percentage of the long-term memory is remembered. Bam! Oh no, it's the dreaded terminology alert. Even though this part of the long short-term memory unit determines what percentage of the long-term memory will be remembered, it is usually called the forget gate. Small bam. Now that we know what the first part of the LSTM unit does, it determines what percentage of the long-term memory will be remembered, let's go back to when the input was 1 and talk about what the second stage does. In a nutshell, the block on the right combines the short-term memory and the input to create a potential long-term memory, and the block on the left determines what percentage of that potential memory to add to the long-term memory. So let's plug the numbers in and do the math to see how a potential memory is created and how much of it is added to the long-term memory. Starting with the block furthest to the right, we multiply the short-term memory and the input by their respective weights. Then we add those values together and add a bias term to get 2.03, the input value for the tan h activation function. Now we plug 2.03 into the equation for the tan h activation function, and we get the y-axis coordinate, 0.97. Remember, the tan h activation function turns any input into a number between -1 and 1. And, in this case, when the input to the LSTM is 1, then, after calculating the x-axis coordinate, the tan h activation function gives us an output close to 1. In contrast, if the input to the LSTM was -10, then, after calculating the x-axis coordinate, the output from the tan h activation function would be -1. Going back to when the input to the LSTM was 1, we have a potential memory, 0.97, based on the short-term memory and the input. Now the LSTM has to decide how much of this potential memory to save. And this is done using the exact same method we used earlier when we determined what percentage of the long-term memory to remember. In other words, after multiplying multiplying the short-term memory and the input by weights, and adding those products together, and adding a bias, we get 4.27, the x-axis input value for the sigmoid activation function. Now,
Brother, what the fuck is this?
long, short.
LSTM networks, or long short-term memory networks, are a type of recurrent neural network designed to handle sequential data while overcoming the vanishing gradient problem. Unlike traditional RNNs, LSTMs use memory cells with gates that control the flow of information, allowing them to learn long-term dependencies in data. This makes them ideal for tasks like speech recognition, language modeling, and time series prediction. By remembering past information for long periods, LSTMs have revolutionized deep learning applications. Follow for more. LSTM networks, or long short-term memory networks, are a type of recurrent neural network
having the multiple layers of neurons and backpropagation. It's a, you have a layer of neuron that goes through a series of intermediate steps to ultimately cognition, and then it'll reverse those steps, go back and forth, and go all over the place. It's interesting, very interesting. It's having the multiple layers of neurons and backpropagation. It's a,
He doesn't know anything about it. Making it up.
There are a few problems with the recurrent neural network, which is solved. There are a few problems with the recurrent neural network, which is solved by this model named LSTM, which stands for long short-term memory. Now, in this video, we will discuss what is LSTM, why do we need it, and what is the problem with the recurrent neural network. Now, this is the model which is a bit hard to understand, especially when you are looking at it, understanding it for the first time. It does not quite make sense what is going on. And same thing happened to me when I learned this concept for the first time. I did not understand much. So after going through a lot of resources, I have wrapped everything into this single video, which will not only give you the mathematical details behind LSTM, but also the intuition behind it, which is very important to understand what is going on. And I just forgot to tell you that at the end of this video, you will find a link to the quiz down in the description box. The quiz is very important to retain your understanding and improve your understanding. So make sure you attempt the quiz. And I hope that after watching this video, you do not need to go anywhere else to understand LSTM. And after watching this video, if you understand LSTM properly, then do hit the like button, show your support, because it takes a lot of time and energy to make such kind of videos. And you also know, why should I repeat it again? Hit the red subscribe button, also hit the bell icon so that it takes this sentence to it to check if it is grammatically correct or not. Now, the individual words will go as an input to this recurrent neural network. But when we pass this long sentence to the recurrent neural network, it acts.
Hi, and welcome to an illustrated guide to LSTMs and GRUs. I'm Lauren Vector, and I'm a machine learning engineer in AI voice assistant space. In this video, we'll start with the intuition behind LSTMs and GRUs. Hi, and welcome to an illustrated guide to LSTMs and GRUs. I'm Lauren Vector, and I'm a machine learning engineer in the AI voice assistant space. In this video, we'll start with the intuition behind LSTMs and GRUs. Then, I'll explain the internal mechanisms that allow the LSTMs and GRUs to perform so well. I'll follow up with an example. If you want to understand what's happening under the hood for these two networks, then this video is for you. LSTMs and GRUs are the more evolved versions of the vanilla recurrent neural networks. During backpropagation, recurrent neural networks suffer from the vanishing gradient problem. The gradient is the value used to update a neural network's weight. The vanishing gradient problem is when the gradient shrinks as it backpropagates through time. If a gradient value becomes extremely small, it doesn't contribute to much learning. So in recurrent neural networks, layers that get a small gradient update doesn't learn. Those are usually the earlier layers. So because these layers don't learn, RNNs can forget what is seen in long sequences, thus having short-term memory. If you want to know more about the mechanics of recurrent neural networks in general, you can watch my previous video, An Illustrated Guide to Recurrent Neural Networks. LSTMs and GRUs were created as the solution to short-term memory. They have internal mechanisms called gates that can regulate the flow of information. These gates can learn which data in a sequence is important to keep or throw away. By doing that, it learns to use relevant information to make predictions. Almost all state-of-the-art results based on recurrent neural networks are achieved with these two networks. You can find LSTMs and GRUs in speech recognition models, speech synthesis, text generation. You can even use them to generate captions for videos. Okay, so by the end of this video, you should have a solid understanding of why LSTMs and GRUs are good at processing long sequences. I am going to approach this with an intuitive explanation and illustrations and avoid as much math as possible. Let's start with the thought experiment. Let's say you're reading reviews online to determine if you want to buy a product. When you read the review, your brain subconsciously only remember important keywords. If your goal is trying to judge if a certain review is good or bad, you pick up words like amazing and will definitely buy again. You don't care much for words like this, gave, all, should, etc. If a friend asked you the next day what the review said, you wouldn't remember it word by word. You might remember the main points though, like it was a perfectly balanced breakfast. The other words would just fade away from memory, unless of course you're one of those people with perfect memory. That is essentially what an LSTM and a GRU does. It can learn to keep only relevant information to make predictions. In this case, the words you remember may
I've been working on this project about visually explaining
how
transformers.
LSTMs and GRUs achieves this, let's review the recurrent neural network. An RNN works like this. First, words gets transformed into machine-readable vectors. Then, the RNN processes the sequence of vectors one by one. While processing, it passes the previous hidden state to the next step of the sequence. The hidden state acts as the neural network's memory. It holds information on previous data that the network has seen before. Let's zoom into the cell of an RNN to see how the hidden state is calculated. First, the input in the previous hidden state is combined to form a vector. That vector now has information on the current input and the previous inputs. The vector goes through the TAN activation, and the output is the new hidden state, or the memory of the network. The TAN activation is used to help regulate the values flowing through the network. The TAN function switches values to always be between -1 and 1. When vectors are flowing through a neural network, it undergoes many transformations due to various math operations. So imagine a value that continues to be multiplied by, let's say, 3. You can see how some values can explode and become astronomical, causing other values to seem insignificant. Let's see what a TAN does. A TAN function ensures that the values stay between -1 and 1, thus regulating the neural network's output. So that's an RNN. It has very few operations internally, but works pretty well. RNN uses a lot less computational resources than its evolved variants. Let's take a look at LSTMs. An LSTM has the same control flow as a recurrent neural network. It processes data sequentially, passing on information as it propagates forward. The difference are the operations within the LSTM cells. These operations are used to allow the LSTM to forget or keep information. Now looking at these operations can get a little overwhelming, so we'll go over this one by one. I want to thank Chris Olah, sorry if I butchered that name. He has an excellent blog post on LSTMs. The following information is inspired by his exceptionally written blog post. I'll include the links in the description. The core concepts of LSTMs are the cell states and its various gates. The cell state acts as a transport highway that transfers relative information all the way down to the sequence chain. You can think of it as a memory of the network. Because the cell state can carry information throughout the sequence processing, in theory, even information from earlier time steps could be carried all the way to the last time step, thus reducing the effective short-term memory. As it goes on its journey, information gets added or removed to the cell state via gates. The gates are just different neural networks that decide which information is allowed on the cell state. The gates learn what information is relevant to keep or forget during training. Gates contain sigmoid activations. A sigmoid activation is similar to the TAN. Instead of squishing values between -1 and 1, it squishes values between 0 and 1. That is helpful to update or forget data because any number getting multiplied by 0 is 0, causing values to disappear or be forgotten. Any number multiplied by 1 is the same value, therefore that value stays the same or is kept. The network can learn what data should be forgotten or what data is important to keep. Let's dig a little deeper into what the various gates are doing. So we have 3 different gates that regulate information flow in an LSTM cell: a forget gate, input gate, and output gate. First, we have the forget gate. This gate decides what information should be thrown or kept away. Information from the previous hidden state and information from the current input is passed through the sigmoid function. Values come out between 0 and 1. The closer to 0 means forget, and the closer to 1 means to keep. To update the cell state, we have the input gate. First, we pass the previous hidden state and the current input to a signal.
Have you heard of recurrent neural networks in machine learning?
No, what are they?
RNNs are neural networks with memory. Imagine predicting the next word in a sentence based on the words that came before it.
Exactly. RNN's ability to process sequential data makes them powerful in speech recognition, stock market prediction, and text generation.
Wow, can you give a math example?
This equation captures how information flows through a basic RNN. XT is the input at time t. HT minus 1 is the output from the previous time step, which acts as the memory of the neuron. Tan H is the tangent function, which squashes the output between -1 and 1.
This means that RNN combines the current input, the past output, and applies a function to it at each step. Have you heard of recurrent neural networks in machine learning?
No, what are they?
RNNs are neural networks with memory. Imagine predicting the next...
Have you heard about a model context protocol in AI development?
Of course, it's like the USB-C port for AI applications. Makes connecting LLMs to different data sources standardized and simple.
So how does it actually work?
MCP follows a client-server architecture where a host application can connect to multiple servers. Trust me, it's tremendous.
Exactly. Think of Pod or any AI tool as the host, then MCP clients maintain connections with servers that expose specific capabilities.
The beauty is you can access local data sources on your computer or connect to remote services over the internet, all with the same protocol.
So it's like having one standard way for AI to talk to any database or tool?
Bingo. With MCP, you can build complex agents without being locked into one LLM vendor.
Plus, all your data stays secure within your infrastructure. No
Literally like learning from this.
To build those AI workflows.
I'm literally learning it from annotate.
You know about hidden Markov models in algorithmic trading?
I know Renaissance Technologies uses it. Their famous medallion fund has been the most successful hedge fund in history.
Exactly. HMM is a machine learning technique. It assumes that there's a hidden state, xt, that changes over time, and it depends only on the state at the previous time, xt minus 1.
Wait, so we can't actually see these hidden states?
Correct. That's why they're called hidden. Instead, we observe something at each time step, yt.
So yt is only dependent on xt?
Bingo. The probability of seeing y of t given x of t is given by pi. This dependency helps us model and predict market behavior using machine learning. Do you know about hidden Markov models in algorithmic trading?
I know Renaissance Tech.
Have you heard of recurrent neural networks in machine learning?
No, what are they?
RNN.
This is the most hardcore machine learning model I've ever built. Based on the 2016 research paper LibNet, which was originally developed by researchers from DeepMind, Oxford University, and SciFar Canada. The amazing thing about this model, it's a professional illustrator. It takes a number of video frames and is able to decode that to determine what a person is saying. With no audio. Insane. I originally started trying to recreate this research on the 24th of December of last year, and only just managed to get it to work. I used TensorFlow and a consumer-grade GPU to be able to get this done in around about 96 epochs. Want to see how it's built? Let me know in the comments below if you want to keep growing. And that's why this is the most hardcore machine learning model I've ever built. This is Baz. He's an AI agent that I'm training to do this level. But right now he's making some bad life choices. It doesn't look that hard though, right? But if he jumps here, dead. He hits this, dead. He runs into this, that's right. No, but if he goes too far, dead. Here's the thing though, I'm not gonna let Baz visually see the game. He's gonna have to do it all based purely on his senses. Now, this game I've been building is all in Godot, and by building, I mean, well, the graphics tutorial. My plan is to train it using a library called Stable Baselines 3. SB3 is all written in a programming language called Python. So how do I get them to talk? After a bit of research, I actually found this, Godot RL. It solves this problem by allowing Godot games to speak through to SB3. It's actually got really good examples, and there's solid documentation. If I run it on a sample, it's almost too easy. So, will this work with Baz? Look, I know I said there was great documentation, but I'll be completely honest. I didn't read it.
Man.
This is how to fine-tune a large language model so you can get it to do exactly what you want, but for cheap. There are a ton of great LLMs out there, and most of them work pretty well, but they're not all that cheap. Look at this. You need to pay for the privilege. What if we could get it fine-tuned for this, and running for this? And what happens when those big LLMs have to pay for the privilege? What if we could get it fine-tuned for this, and running for this? And what happens when those big LLMs don't quite work? This happens more than you think. It's usually when you've gone down a really specific rabbit hole on a niche topic, and no matter how good that LLM is, it loses the plot. Little like this. What if you could apply a knowledge cartridge to that LLM and inject the right knowledge for specific use cases? This is what fine-tuning aims to do. But all fine-tuning is costly and it takes time.
LoRa, a low-rank adaptation, is like plugging in a new game type. We're able to add in the specific knowledge that we need without having to go through the extensive cost or time of retraining all of the existing LLM parameters. And by running a quantized version of it, you can get it to run fast on any old laptop, like my MacBook here. I'm going to take you through a complete end-to-end walkthrough on a custom training dataset in under 60 minutes. But do I need to use a massive LLM to do this? And what if you only have PDFs or text or code? How do you use that for training? And are there specific training parameters that AI engineering pros use? I went down the rabbit hole with this, and you'll see a little later on that I did well over 15 training runs to get this workflow developed. But it means that it's ultra straightforward to train your own QLoRa now. On this positive note, I'm going to break this down into 7 stages. First up, how bad is the LLM hallucinating? So my first job in tech was actually as a technology consultant focused on a tool called TM1. Now it's a little bit of software that's mainly used for finance teams. Basically, it's like Excel on steroids. Now, I want to see how much I can teach an LLM about TM1. Now, keep in mind, just because I'm using this data doesn't mean you need to. Later on, I'm going to show you how to use your own data. So what exactly makes LoRa so unique? Well, imagine full fine-tuning looks like this. In order to fine-tune the model, we need to update the weights in this white matrix. This parameter update is updated by this pink matrix. Note they have the same size. If we take an example which has 8 rows and 8 columns of weights, that means 64 parameters to update. LoRa, on the other hand, is usually represented like this. It's made up of 2 weight matrices for every one you choose to tune, the lower matrix A and the upper matrix B. A key hyperparameter in LoRa is the rank of the matrix. This basically dictates how large the adapter to the LLM will be. Higher rank equals more parameters to update. Let's say we set the rank for this adapter to 2. This will give us matrix A, which has 2 rows and 8 columns, so 16 parameters to update, and matrix B, which has 8 rows and 2 columns, also 16 parameters to update. That's 32 parameters to update in total. But there's a problem. The dimensions of the weight need to match the original white pre-trained weights in order to add them together. And remember, these are 8 by 8. If you look at the dimensions of A and B here, they don't quite match. How do we fix this? Well, if you find 2 outlying questions that I've gone and predefined. The first question is, what is a pick list in TM1? And the answer to that is a list of valid values for a specific element or a cube cell. So it's effectively a drop-down. Second question, what is the minimum number of dimensions for a cube in TM1? In this case, it is 2. I think this one's going to be really interesting, right? Because a cube would typically have 3 dimensions. So we'll see if we can train that into the LLM. The third question, how do I create a dimension? So you can open up a dimension editor, insert different elements. So basically allows us to define a perspective inside of our cube. Now, our fourth question, this one's a little bit airy-fairy, but we'll give it a crack. What are the core advantages of TM1? Runs in memory, it's extremely quick, you're able to model complex business logic, you can integrate with ERPs, CRMs, APIs, so on and so forth. Now, I'm going to use a pretty small LLM for this, namely Llama 3.21b. This means that it's small, fast, and can be updated for pretty cheap. I think it works out costing like 50 cents to $2 to fine-tune, so then you can run it locally on your machine, which means it's kind of free. Now, I'm going to run this using Langflow and Olama here. You can install it by running this command in your terminal and run it by running this command. Right, let's run through the baseline questions. So I'm going to open up the playground and we can create a new chat. Just keep in mind, I'm currently running this on Llama 3.21b, so this is a completely unfine-tuned model. So if we go and also, I want to say that I'm using top k is equal to 1, which basically means that we should be using greedy decoding, so not a hell of a lot of creativity. So I'm going to open up the playground and let's open or run our first prompt. So what is a pick list? TM1. If we go and run that, so we've got a set of responses. So in TM1, tallyman1, a pick list is a set of predefined values or options that can be selected from within a form, report, or other business object. It's essentially a predefined set of choices that can be used to narrow down a selection. This actually isn't too bad. In TM1, pick lists are often used to restrict
I think I'm done.